Aloha everybody, this is Gigi from Kauai Community College. This video will talk about a few strategies for multiplication in base 10. So you have seen multiplication before. The definition of multiplication is going to be as repeated addition. For example, 5 times 3 is 3 plus 3 plus 3 plus 3 plus 3 repeatedly 5 times, right? Visually, we can see in a set model as 5 groups of 3. Now, to make the calculations, we may look at a jumping method. So we're counting, skip counting by 3. So we would be 3, 6, 9, 12, 15. So the answer is 15, right? Okay, so that's how we would develop the idea of multiplication. Now, then visually we can see multiplication in an array and an area model. And these are two very good models to explain the any order property, right? For example, 3 rows of 5, 3 rows of 5 is 15 ladybugs, right? Is the same, if you count up the number of ladybugs, would be the same as 5 rows of 3. So this is 3 times 5 is the same as 5 times 3. So it seems like we have an any order property here for multiplication. And when we actually learn about, so we start looking at these things as an array, which looks kind of like a rectangle if you can visualize that, but that doesn't come until later when we learn about area of a rectangle. So when we do learn about the area of the rectangle, we would say a 3 inches by 5 inches rectangle, a 3 by 5 have an area of 3 times 5, 15 square inches. But if you go ahead and turn the rectangle around sideways, or if you just turn your head sideways, you will see that the area would be still the same. So again, 3 times 5 is the same as 5 times 3. So we have the any order property for multiplication. So you can switch any order you want, right? All right, now the one property that is really awesome, and it's being used to really create many other strategies for multiplication, and that property is called the distributive property. And how do you know the distributive property? It's multiplication over addition. Here is what I mean by that. If we are looking to count how many penguins there are, we would look at it as 1, 2, 3, 4, 5, 5 rows of 1, 2, 3, 4, 5, 6, 7, 8, 9, 5 rows of 9. Okay, so 5 rows of 9. Now, if I didn't know what 5 rows of 9 is, I may want to split this up into smaller arrays or rectangles, depending on how we want to visualize that. What if I just go like this group and then that group? Okay, so the first group is going to be 5 by 1, 2, 3, 4, 5. 5 by 5. And I know that 5 times 5 is 25, right? And then the second part would be a 5 by 4. Okay, so then I would say 5 times 9 is the same as 5 times 9 is being split into 5 plus 4. Okay, and that is then I would say then to count this, I would say first I would say 5 by 5, and that give me 25. And then I would say now I have a 5 by 4, and that will give me 20. So this is equal to 5 times 5 plus 5 times 4. And that is what we call the distributive property. It's multiplication over addition. So we have to distribute the outer 5 into each one of the things inside. So that would be 25 plus 20, and that is 45. All right. Now, instead of looking at it in two arrays or two rectangles, I can go ahead and look at it into even smaller rectangles. Let's say if I would do this. Now we see that there are 4 rectangles, right? So instead of having this 5 right here, the 5 is being split into a 3 and a 2, and then the 9 is being split into a 5 and a 4. So I have 4 rectangles to do. So then what I'm saying now is 5 times 9 can be the same as 3 plus 2 multiplied by 5 plus 4. And that's a plus right there, not multiply. Okay, because 5 is 3 plus 2, and 9 is 5 plus 4. Well, how do I go and calculate that? It's a 3 by 5 rectangle here, so that would give me 15. And then it's a 3 by 4, that give me 12. And then this is a 2 by 5, and that give me 10. And then this is a 2 by 4, and that give me 8. Okay, but I want to look at the process and not particularly the actual answer there. How does that work? First, I have to say 3 times 5 and then 3 times 4. That's the top 2 rectangles. So this is the same as 3 times 5 plus 3 times 4, and then plus 2 times 5, and then plus 2 times 4. Okay, so there are 4 parts there. Okay, and that is what we call the distributive property. Now, let's see how the distributive property works for larger numbers. 34 times 27. Now, if we just see it as 34 and 27 as 20 plus 7, then I have 2 sub-rectangles, and that would be 30 times 20 and 34 times 20 and 34 times 7. Okay, and that would be 680 plus 238, and that is whatever that answer is. Now, the same problem, but what if we see 34 as 30 and 4, and 27 as 20 and 7, then we would have 4 different rectangles, right? 4 different things. In other words, we can break up 34 as 30 plus 4, and then 20 as 20 plus 7. And you saw earlier that the 2 by 2, the 4 little rectangles, it's kind of complicated to keep track of, right? So here it goes. First, we would have to take 30 times 20. That would be 30 times 20. And then we would have to take 30 times 7, 30 times 7. And then we would take 4 times 20, 4 times 20, and then 4 times 7. 4 times 7, okay? And that is how the distributive property works. And if you put in some teeth right here, you will see my friend Freddy Foil. That is what we call that in an algebra class. There's Freddy Foil. Here are his eyes and his nose. Do you see Freddy Foil? And what does foil mean? First, outer, inner, last. And that is how we get Freddy Foil. What exactly does that mean? You got to distribute it and get 30 plus multiplied by 20, and that gives us 600. 30 times 7, that's the outer, that gives you 210. The inner is 4 times 20, and that will give you 80, and then 4 times 7, that's give you 28. Well, seeing this, you might be saying, oh my gosh, why is multiplication so complicated? Well, really, it doesn't have to. We just have to figure out how to represent the information in a clear manner once we understand how the distributive property work, right? So really, in an elementary classroom, you'll be looking at either the area model or the partial product model. Okay, so either one would actually shows you how the distributive property works for multiplication. That would be multiplying over addition. So for the 34 times 27, we will already see, but I'm going to show you that one more time just to see how clean this could be and how awesome this is, right? So 34 is going to be 30 plus 4. 27 is going to be 20 plus 7. So then the answer to this problem is the area of the whole entire rectangle, the larger rectangle. And this would be a 34 by 27 rectangle, right? So the area of the big rectangle is the sum of the areas of all of those other ones inside. So let's go and find out the area of all of those inside. 20 times 30 is 600. 20 times 4 is 80. 7 times 30 is 210. 7 times 4 is 28. And then we would go and add together because the area of the big rectangle, which is the answer to 34 times 27, is the sum of all of these sub-rectangles there. So we have 34 times 27 is 918. Okay, so that's how the distributive property works. As you saw earlier, it's just in a very nice, organized manner in a area model, area of a rectangle. Okay, now distributive property also works in what we call a partial product presentation. It looks like, to begin with, looks like the old-fashioned way, but we're not gonna think of it like the old-fashioned way. We're gonna think 34 is 30 plus 4, and 27 is 20 plus 7, as we have seen on the left-hand side here in the area model, right? Except for, instead of drawing an area model, we just write them out vertically. So we have first 30 times 20 is our first partial product. The second partial product would be 20 times 4. So you take 20 and you multiply to each one of these. And then you take 7 and you multiply to each one of these. Just like Freddie Foil, okay? Except for we're not going to write it horizontally, we're writing it vertically. And here we would have 7 times 30 as another partial product, and then 7 times 4 is another partial product. So when you have a 2 by 2 rectangle like you see, we would have 4 sub-rectangles or 4 partial products. And partial products are 600, 80, 210, 28. Just like what you saw over here in the area model, except for it's organized in what we call partial products way. And then in order to get the answer, it would be the sum of all partial products, and that would be 918. Same. Just the presentation is a little bit different. One in an area model, one in the partial product model. But both really are emphasizing the idea of the distributive property. Okay, that's the mathematical property that will make this work. Okay, so after we learn about multiplication, learn about these strategies, we're starting to compute or starting to feel pretty awesome about ourselves. We start to be a little bit more flexible with our thinking. So we might develop thinking strategies. For example, the over and or the under strategies. Okay, here's what I mean by that. This is when I see something like this, I could think of maybe going over. What does that mean, going over? Well, 18 multiplying by 18 is kind of hard. So I'm going to go and multiply by 20, right? So that means I'm going over the product. I only needed 18 copies of 24, but I'm going to go ahead and multiply by 20. Well, then if I'm going to go over, then I need to take some out. Like how many? Instead of 18, I used 20, so now I had an extra 2, right? So now I'm going to go and think 24 times 2 is 48. So overall, I would say 24 times 18 must be 480 minus 48, whatever that is. So that is what it means by going over. You're trying to go to a nice number, and then since you're going over, you're going to subtract that the rest of it out. Okay, now here, when I see a problem like this, 27 times 16, I'm looking at 27, and I'm like, oh, I wish I have 25. So I'm going to go under and think 25 times 16. And that's easy for me to think because I know 25 times 4 is 100 because I know 4 quarters is $1. Okay, so then in 25 times 16 is going to be 4 times as many as this, which would give me 400. And that is how mentally how I'm going to work that. And that's just so much easier, right? Well, I went under. So I need more. How many more? 2 more copies of 16. So 2 times 16 is 32. So since I went under, I'm going to have to now go and add in some more. That means 27 times 16 is going to be 400 plus 32. Like, so that is a thinking strategy. That's like mental, like, you know, I mean, honestly, it's pretty mental the way my brain works just right there. But once you are more comfortable with multiplication or any operation, you would begin to think about different ways to make computation a little bit quicker and more efficient, and you're going to become more flexible, and that is what we call number sense, right? So having the number sense means having a lot of these thinking strategies on your belt so you can just pull them out as you go. Okay. But overall, I would say, hey, the area model and the partial product, if you have to show your work, are probably the most beautiful thing that you've ever seen. I mean, that's so awesome. It displayed the distributive property in a very organized manner, right? Now, if we really have to, we could go and look at the old-fashioned. I mean, you might be thinking, why are we learning all of these new things? Because it's mathematically correct. It's conceptually shown, right? But let's just take a look at 34 times 27, the old-fashioned way. I'm not sure if I actually know how to do that. Let's see. Okay, so we'll start with 7. 7 times 4, we would say, is 28. So you write an 8 and you put the 2 right there, right? Not sure why that is. Let's think about that for just a second. And then 7 times 3 is 21. And then 2 more is 23. That's the old-fashioned way. And then you would go 2 times 4 is 8. But you don't put it there. You actually put it here. And some people put the 0 right there. Some people don't. I'm not sure. And then 2 times 4 is 8. And then 2 times 3 is 6. And then we would go and add. So then we'll have 8. And then 8 plus 3 is 11. So you go 1 here. Put the 1 right there. And that will make it 9. Now, that's the old-fashioned way. And honestly, when I am doing this, I am saying so many wrong things mathematically. Okay, and this is what I mean. We're going to go ahead and revise this old-fashioned way. And I call this the old-fashioned with a twist. It's look kind of like the old-fashioned, but we're going to put a little twist to that. And what I mean by that is we are going to speak mathematically correct. Here is what I mean. 27 is actually, the 2 right here is not 2. That's 2 tens, right? It's 20, right? So when we are multiplying, we're actually thinking, instead of starting right here at 7, I'm going to go ahead and start with the 20. So first I would think 20 times 34. So 20 times 34, I'm going to have a 0 right there. And then 2 times 34, what will give me 2 times 4 is 8. And 2 times 3 is 6. Okay, so now I get that that first number there. And then 7 is just the singles. That's just really is 7. So I can go 7 times 4 is 28. And I could now say, carry the 2 over to the second place value, right? And then 7 times 3 is 21, and then 2 more is 23. I don't know. Why is that better? It's just really because I am thinking about this as place value. Okay? Or you can just go ahead and use partial products or the area model. But the most awesome thing ever. Like, why not use that instead of the old-fashioned where it's so confusing, right? And it's confusing because it's just an algorithm. It's just, this is what you do to get the answer rather than having your work shown as how it should be mathematically, meaning the distributive property is being displayed in the area model and the partial products. And that is it for me in strategies and for multiplication.